Wanted to work through a couple of examples that involve self-inductance. Self-inductance is a characteristic property of a circuit, or self-inductance is a characteristic property of a circuit component. In the first example here, we're going to calculate the self-inductance of a coil from the relationship between the cause of self-induction in the coil and the result of self-induction in the coil. So there's self-induction in the coil if the current is changing in the coil. The result of the self-induction in the coil is the appearance of a induced EMF in the coil. So the current changing is the cause and the induced EMF is the result. And we're going to use the relationship between those two to figure out the self-inductance. Then in the second problem, we're going to think about a solenoid. The self-inductance of a solenoid or other circuit component is determined by the geometry of the solenoid or whatever circuit component. And for a solenoid, we can write down a simple formula that relates the self-inductance of that solenoid to the geometry properties of that solenoid, to the number of turns of the solenoid, the length of the solenoid, the cross-section of the solenoid. And so that will be our second example of calculating self-inductance. So let's start with the first one. This is question 1 here. We're told that a current in a coil decreases from 3.5 amps to 2.0 amps in a duration of half a second. So that will be the cause of self-induction. We see that in the coil, there is an induced electromotive force that is 12 millivolts. That would be the result of this self-induction. And we've got to calculate from those two pieces of information the self-inductance. Well, the equation that we want to solve this is really a version of Faraday's law of induction. It's this version here which relates the cause of the induction, this is the changing current on the right-hand side, to the result of the induction, this is the induced EMF on the left-hand side. Now in this problem, we know both the cause, the changing current, and we know the result, the induced EMF. We just have to rearrange this equation for the self-inductance, L. And so the self-inductance L is just the induced EMF divided by the time rate of change of the current. The induced EMF is 12 millivolts, so that's 0.012 volts. And that's divided by the rate of change of the current, which is the current changed by 1.5 amps. And that change occurred in half a second. And so actually the rate of change of current is 3 amps per second. Well, if I take 12 millivolts, divide it by 3, I'm going to get 4 millihenries, or 0.004 henries. So let me just write that as 4 millihenries. And so that, from that relationship between cause and effect, the changing current and the induced EMF is the self-inductance L of the coil. Now, let me just make one last point about the way I solved this problem. I did not worry about plus or minus signs or the directions of the currents or the senses of the induced EMF. So I was working with the size of the induced EMF, the size of the change in current. So when I did the calculation, I just put in the size of the change and the size of the EMF and got 4 millihenries. That's the self-inductance. The second problem asked us to calculate the self-inductance of a solenoid, not based on this relationship between cause and effect, between changing current and induced EMF, but rather from the geometry of the solenoid. So in this particular problem, we're told we've got a 200-turn solenoid. It has a length of 5 centimeters, has a cross-section of 4 square centimeters, and we've got to calculate the self-inductance L. So if I was to picture this solenoid, here we are. Here's the kind of windings of the solenoid. I'm not going to draw 200 of them, obviously. Here is the length of the solenoid. That's 5 centimeters, we're told that. Here's the cross-sectional area of the solenoid. That's 4 centimeters squared, we're told that. And the number of turns of the solenoid, that was 200 turns total. So those geometrical characteristics, those geometrical properties of the solenoid determining the solenoid's self-inductance. So that would determine, if you change the current by this or that amount, the induced EMF corresponding to this or that change in current. So let's go ahead and calculate the self-inductance. The formula for the self-inductance can be written as mu naught lowercase n squared times A, the area of the, or the cross-section of the solenoid, times the length of the solenoid. So all the quantities over here on the right-hand side, they're all about the geometry of the solenoid. Remember that lowercase n is our notation for the number of turns per unit length. So it's not the total number of turns, that's 200. It's the number of turns per unit length. So in our particular case, we've got 200 turns in 0.05 meters. So actually the number of turns per unit length is 4,000 per meter. Anyway, with that information, we can start plugging the geometry into this equation for the self-inductance. So mu naught, that's that constant that characterizes the strength of magnetism, is 4 pi times 10 to the minus 7 Tesla's meters over amps. N, that's 4,000. And it's n squared. The area is 4 square centimeters. So there's 100 squares, there's 100 centimeters in a meter. There's 10,000, 100 squared, square centimeters in a square meter. So the area is 4 centimeters squared, or 4 times 10 to the minus 4 meters squared. And then finally, the length of the solenoid, running out of room here, is 0.05 meters. So if I multiply all these quantities together, that gave me, I've already worked this out, obviously, 0.40 millihenries. That's 4 times 10 to the minus 4 henries. And that's the self-inductance of that solenoid. Anyway, that was an example, well, that was 2 examples about calculating self-inductance. One of them calculated the self-inductance of a coil from the phenomena of self-inductance. and the relationship between induced EMF and the changing current. And the other one calculated the self-inductance of a solenoid from the geometry, the properties of the solenoid.